So in this series of videos, we're going to be switching our focus from what's been so far just be looking at point estimates, that is our single estimate of the mean, x bar being an estimate of mu, s being an estimate of sigma, p bar being a estimate of pi. Right, in each of these cases, we're going to be moving from that single point estimate into looking at instead a confidence interval, that is to take a look at all kind of the likely values that this could actually be. And while point estimates are important, it is also important to recognize the fuzz, that air that exists around them, the fact that likely any one point estimate we pull out, it's likely close to the true population parameter, but likely has some air into it, could very well be some distance away. So altogether in today's video, or in today's series of videos, we're going to be taking a look at first confidence intervals around our sample mean. Well, first, I guess we have to introduce what a confidence interval is, moving into confidence interval around our sample mean. From there, we'll do the same around the sample proportion, and then we'll finish off the video by introducing a new distribution altogether. This will be known as our student's t-distribution, and with that student's t-distribution, that is going to work out for our confidence intervals anytime we're sampling our sampling mean, right? So x bar, but we don't know what the true population mean is. So sampling distribution of x bar when sigma is unknown. That becomes a bit of a tricky situation to work with, not mathematically, not conceptually, but it becomes tricky because in the questions we now really need to ask, do I know my population standard deviation or do I not? Do I have to estimate it? And if I have to estimate it, well, I need to change things a bit. So let's go and jump over. Let's take a look at the first bit. Let's introduce this whole concept of a confidence interval. So to start off with this, let's take a look at just our sample mean. We have a distribution of x bar. Let's use a bright color for this. We have x bar, and we know that x bar itself, that is our sample mean, is a random variable. That is, every time we pull a sample out of a population, we're going to get a different average. Right, and we talked about this in saying we want to find the average height of everyone in the classroom. There is an average height in the classroom, that's the population average, but if I kept pulling out random samples, every time I pulled out a random sample, I'd get a different value of x bar. Fortunately, right, although every time I pull out x bar, I'd get a different one, it is normally distributed, and it is normally distributed centered around the true population mean and with a known standard error. That is, the standard deviation of our sample means is equal to the standard deviation of the underlying population, x, all over the square root of n. And so, okay, normally distributed, centered around the true population, and we see that, hey, every time I go and I pull out a random sample, I could get a value of x bar right there, right? I could get a value of x bar very extreme. I could get a value of x bar way out over there. I could, right? And typically, right, we see the height. This is like the relative frequency, the probability of getting one in that area. We see that the most likely area to get a value of x bar is somewhere like that. But importantly, what we're going to witness with this is that we have these values of x bar. And if we kind of just were to drag these down to kind of take a look at, let's go that guy down, and this guy down, is that attached to each of these values of x bar is some uncertainty, right? This uncertainty as to how close this sample mean is to the true population mean. Is it a really good estimate of the true population mean, right? X bar. Or is there a lot of uncertainty? Did we get way out there just by dumb luck, pulled out a sample of all extremes and ended out way out here? What a confidence interval tells us is that if we were just to continually resample x bar, resample x bar, resample x bar, we could work out the fuzz around this x bar such that, right, if we worked out fuzz like this, we'd say, okay, x bar plus or minus some number, x bar plus or minus some number, right? And we did this for all of these. We calculated value of x bar. We worked out, hey, what is a typical sampling error? How far would we be falling away from our mean? We can work out a level of confidence that if we were to continually do this, continually sample, if I say calculated a 90% confidence interval, so this confidence interval, that's this band around X bar, what this 90% confidence interval is saying is that 9 out of 10 times my value of X bar plus or minus my band would cover the true population mean, right? And that is, right, our true population mean. If we take a look at that, there we go. That is covered within this band, right? This fuzz, this uncertainty around this sampling mean, right? So in a 90% confidence interval, these bands are wide enough such that in 9 out of 10 times, these bands would cover that true population mean. Which one does? Which one doesn't? Well, we don't actually know that, right? That's the nature of sampling. We don't know, hey, which out of these is actually covering, which one doesn't. But what we can be sure is that, hey, 9 out of 10 samples, plus or minus the fuzz, will actually capture that true population mean. So, okay, how about do we go about figuring this out? How do we go about calculating this confidence interval, this fuzz around our estimate of X bar? Let's go work it out. So let's say that we have some sample pulled out. We'll say we have a sample mean pulled out of 50 from a population with a standard deviation of X of 25. We then have a sample, right? We've pulled out, we'll presume this is from a normal distribution just to make this easy. We'll say that, hey, we pulled out a sample size of size, let's say we've pulled out a sample size of size 25 as, let's say 16. 16, there we go. That way we just don't get confused with those guys being the same number. Okay, well, if we went through this, well, what we could look at is we could say, okay, our normal standardization formula, Z equals X minus mu all over, well, standard deviation of X all over root N. Sorry, that is X bar minus mu. I'm dealing with the distribution of sampling means. And if I look through this, I'm saying in this case here, I don't know what my mean is. Right? I know, hey, this is my sample mean. For some reason, I know what the true population standard deviation is. Right? So check, I know that. I know what my sample size is. I've calculated my sample mean, but I don't know what the population mean is. That's unknown. I'm not sure as to what this is. Well, I can work out some fuzz around my value of X bar in order to figure out, well, likely my value of X bar would cover it. And let's see how we would do that. Really, all it's going to be is just an algebra game. So first thing, let's do Z times our standard errors. So we would have Z times standard deviation of X all over root N, and that's going to be X bar minus mu. What we then want to do, I don't want minus mu, I want to get the actual value of mu, so I'm just going to switch those two to each side, and what I'm going to get is mu equals X bar, and then what I'm going to want to do is I'm going to actually want to include a plus or minus because I want the fuzz on both sides. That is, essentially, I want both the positive and negative value of Z to be included here. Sigma X all over root N. And okay, now I'm saying, hey, I can calculate where mu could be within some band based off of some degree of confidence. So, okay, great. We say, hey, looking at our question right now, we have everything we need. We have X bar, check. We have sigma, check. We have our sample size, check. But we're missing this Z value. What the heck do we do for this Z value? Well, this Z value is going to be based off of the degree of confidence that we want. That is, do I want this band, right? Keep in mind that's all this is. This is some value of X bar plus or minus some fuzz. So X bar plus some fuzz minus some fuzz, right? Some uncertainty, some band around that. That's this guy right here, X bar plus fuzz minus fuzz. That's what this plus or minus is. I'm going to want to set Z based off the level of confidence that I want. If I want this band to cover the true population mean 99% of the time, well, then I'd pick a value of Z appropriately. If I wanted this band to cover 90% of the time, well, then similarly, I'd pick a value of Z appropriately. But okay, what is that appropriate value of Z, right? How exactly do we figure that out? Okay, let's talk about that. Let's talk about that. Let's scroll down a bit. Let's suppose that I want it for this whole 90% level of confidence. That is 9 out of 10 times when I calculate this, pull out a sample, get a value of X bar, 9 out of 10 times this value of X bar plus or minus the fuzz will cover the true population mean. For Z, okay, what's going on? I'm going to want a value of Z such that, let's just visualize this. There's my mean. And I want, right, we don't even know what that mean is. We don't even know what the standard deviation is. I want a case such that this whole bit in the middle is 0.95. That is 95%. That is this tail out here. Well, that tail there is going to be 0.025, and this guy here is similarly going to be 0.025. Okay, how do I find these values of Z, right? How am I going to work this out? Well, the way that I'm going to work this out, there's my Z, is I want to find what is this value, and the way that I do that is say, hey, some value of Z to the mean, some value of Z to the mean, such that, hey, this whole thing is 0.95, so symmetric, right, symmetrically split. So if I do my confidence interval, 95% confidence interval divided by 2, I'm going to get, hey, I want 0.475 there, 0.475 there. And now what I need to do is I just need to go into the meat of my stats table, find that probability, and then work out backwards to find that corresponding Z value. So let's jump over, let's take a look at how we would do that. And let's bring the table up so the screen will flash white, so just be careful, it will get really bright in a second here. 0.4750 is what we're looking for. So, okay, in the middle of the table here, we're looking for the probability. We're looking for right there, that guy, 0.4750, which is 1.9, go up, 1.96. Great, so we have our Z value, 1.96. And then keeping in mind, looking at that, we want both the plus or minus, so we have 1.96 and negative 1.96. Giving us a 95% of observations will fall within that band. Okay. Oh, look at that. Look at that. I completely messed up. Here I said, hey, we want a 90%, and I went and calculated 95%. Great. So we have that value for 95%. What would we do for 90%, right? We've seen that. Same idea, right? Let's just go through this again. A little bit of a mistake, but hey, learning chance, learning opportunity here. How do we do it for a 90%? Exact same process. Exact same process. So we'd have our distribution. There's our normal. So Z centered around 0. And in this case, I want a 90%. So again, two extremes, one all the way over there. That's my negative. That's my positive, such that for a 90% confidence interval, this area in between would be 90%. That is, again, similarly working that out between this Z and the mean. Between this Z and the mean is going to be half of that. So 0.9 divided by 2, 0.4500, 0.4500. Okay, so we have the probability. We want the Z. Let's jump back to our Z table. Let's go look that up. So if we do that, we are going to have, we're looking for 4500. It's going to be pretty similar to where we just were. 47, 458, 45, 45, 45. Oh, here we go. Oh, we have, interestingly enough, we have with our Z table, we are perfectly split, right? We don't have a closest value. We are perfectly split between 4495. Let's go make that guy pink just so we can reference that. And 4505. We're perfectly split between these two, right? There's not one that's closer to say, hey, let's go to the closer one. So, okay, what do? This is a case where we really just want to completely split the difference, not even arguing about it to say, hey, this one's closer, let's just use the closer value. No, we're perfectly split. What we're going to do is we're going to go 1.64, and then we're going to split the difference between 4 and 5, so we're going to go 1.645. And that's what we would use for our Z value. So let's go through that in. So that'd be both plus or minus 1.645 and negative 1.645. And that would be the corresponding Z value that we could use for our confidence interval. So, okay, we want 90%. Cool, we accidentally worked out the 95% first. Great, we now know those Z values. Let's go for the 90. So here's our question. We want the confidence interval of this value of X bar around the population mean for a 90% level of confidence. So let's calculate that. Let's calculate this X bar plus or minus the fuzz. So X bar is 50 plus or minus, what did we say our Z value was? For a 90% confidence interval, we said that was 1.645. And then I have my standard errors. Standard errors are going to be a standard deviation of 25 all over root 16. So if I work that out, my confidence interval is going to be 50 plus or minus 10.28. Right, so this is my value of X bar, 10.28, right? That'd be plus 10.28 minus 10.28, giving me my range as to values in which my true population mean would be, such that, hey, this band would cover that true mean 9 out of 10 times. So, okay, that's not actually how we would display our confidence interval. The way we would display our confidence interval is square brackets. We would do the lower band, upper band. So the lower and extreme, lower extreme, high extreme of what this works out to be. So lower extreme, 50 minus 10.28. Well, 50 minus 10.28, that's going to give me 39.72. Higher extreme, 50 plus 10.28, that's going to be 60.28. So there would be my 90% confidence interval around my sample mean, saying that, hey, there is a decent chance that my true population mean is somewhere within here, giving me my likely fuzz of uncertainty of this estimation, right? Keep in mind, this is just an estimation, right? It's an estimate as to what that true population mean is, and this is my uncertainty around it, that fuzz, so to say, from my estimate. And in this case here, the bigger the range, well, the more uncertainty, the more fuzz there is. The smaller the range, right, the more tightly packed these two values are, well, then the more accurate of an estimation we have. And that's one of the things you want to look at. Let's just compare though quickly, because one of the other ways that we'll see, this is a 90% confidence interval, so 9 out of 10 times value of X bar would cover the true population mean. Let's see how things change if we just updated this. Same sample mean, same standard deviation, same sample size. Let's just see if we updated this to be a 95%. So in this case here, we would have 50 plus or minus 1.96 and 25 all over root 16. So again, 25 over root 16, that's going to be 25 over 4 times 1.96. That's going to give me 50 plus or minus 12.25. right? In this case here, we see that as our confidence interval increases, so does our fuzz. If we want to be increasingly confident that we're covering that true population mean a good chunk of the time, well, we need wider and wider and wider fuzz in order to be increasingly confident. So yes, I'm more confident that this is going to be covering that true population mean, but we see that with it comes more uncertainty as to where that might be. We have on the lower side 50 minus 12.25 yielding 37.75, and on the high side we have 62.25. So we see my band has gotten wider, right? Much, much wider, and as a result, much more likely that any one value of X bar is going to cover that true population, right? In this case here, 95% confidence interval. Well, in a 95% confidence interval, this is only going to be 1 out of every 20 that does not cover my true population mean. Question, do I know whether or not my true population mean is between these values? No, I don't. This could be, right, this value of X bar, that value of X bar could be that 1 out of 20 that was so extreme that it's not being covered. That's unlikely, right? There's only a 5% chance that I got that sample, but it could exist, right? It could exist. So all it's saying is that it's very likely that I've pulled out a sample, right? 19 out of 20 times I would pull out a sample. 95% of the time I'd pull out a sample such that, hey, this is true. This covers the true population mean somewhere within that band. So that's our confidence interval. That's the idea behind it, this level of fuzz or uncertainty. That was an example there of our confidence interval for, so let's go here. That was our confidence interval for X bar when sigma is known, right? That is when we know the true population standard deviation. And so far that really doesn't seem too special because so far in this course we've always known what the standard deviation of X is. We've always had this given. We will relax that assumption as we move on, and we'll take a look at how things change as we get to that point. What about steps? What about steps for our confidence interval? Okay, so our confidence interval around mu is X bar plus or minus Z all over our standard errors. Right, and again, oh no, it's a new formula. Right, keep in mind all we did is we just rearranged that standardization formula to get this guy. In this case, X bar will always be given to you, or you can calculate it, right? If I just gave you a list of numbers, 6, 3, 4, 1, and 10, well, you could calculate your sample average. You could then say, hey, we have 1, 2, 3, 4, 5 numbers. Well, n is 5. I would have to give you the true population standard deviation, right? So sample mean, sample size will always be given to you, or you'd have to figure it out from raw data. Population standard deviation will always be given to you. Z? Z will always be what it needs to be for the confidence interval of interest. And commonly, we'll use 99% confidence intervals, 95%, or 90%. This is typical convention, but it doesn't have to be, right? And we've already calculated this. This here, 90%, that is a Z of plus or minus 1.645. 95, well, that there is a Z of plus or minus 1.96. And then 99, what is that going to be? Well, we could go look that up. 99%, so 99 divided by 2, that's 49.5. So if we went to our table again to look that guy up, we would want to find 0.4950. So going through here, it's going to be pretty close to the end. 0.49, again, we see that it's split right in between the two. So we get 2.575. 2.575 would be that case there. So Z is plus or minus 2.575. Now, okay, yes, those are our confidence intervals. That's the Z values for those common confidence intervals. Don't fall into the trap that a confidence interval has to be one of those three. We could very easily say, hey, what is the 86% confidence interval of the population mean? What is something like a 60% confidence interval, right? Any confidence interval at all we could ask for. Yes, these are the common three, but we could ask for literally any percent confidence interval. And the way we would always do that is we would take our confidence interval, so 86 over 2, giving me what? 86% over 2, so 0.86 over 2 being 0.4300. Once we have that probability, we would go to our table, we would look up in the meat that probability there. So hey, let's just do that just for fun. 0.4300, what would that guy work out to? Let's find that. So 0.43, 0.42, 44, 4306. That looks like that guy there would be our closest. So that would give me 1.48. Right? 1.48 is what we could work out there. So that would be a Z of plus or minus 1.48. Just as an example as to how we could work that out. So we do that, we throw that in, and then through that we can say, okay, here's my point estimate. Here is my fuzz, or my uncertainty, right? That uncertainty around that point estimate, such that I can say, okay, within some percent of the time, this point estimate plus or minus the fuzz will cover the true population mean. That's our idea. That's our big takeaway for a confidence interval. Outside of that, they're rather mechanical in practice. So what we're going to do, we're not really going to jump into many examples of this right away. We're just going to carry on and we're going to be taking a look at a confidence interval for the sample proportion. So let's take a look at that next. So confidence interval for the sample proportion, same kind of thing needs to happen, right? So first of all, we kind of glazed over it. Let's just jump back and take a look at that. Hey, for X bar to actually be normally distributed, we had to have our central limit theorem actually hold. That is, we had to have n be greater than 3, n be greater than 10, or n be greater than 30, depending on our assumptions or our knowledge of the population, right? N greater than 3 if our population was normal, n greater than 10 if our population was symmetric, and n greater than 30 or equal to 30 if population is anything, right? Anytime we have a sample size bigger than 30, we're just golden, we don't need to worry, right? This had to hold, this had to be true in order for us to do a confidence interval, in order for us to use that Z, right? Z is based off the standard normal. If this is not true, then X bar is not normal. If X bar is not normal, we can't use a Z. So, okay, that basic assumption needed to be met. If that was, yes, we could go through for our confidence intervals. In this case, we're looking at the distribution of our sample proportion. And we saw, hey, our sample proportion is, again, normally distributed, centered around the true population proportion, pi. You'll also sometimes see this just as p without the p bar. And in this case here, this is true if NP and Q are greater than or equal to 5. And or other binomial conditions are met too, right? So such that, hey, X is discrete, it is either success or failure, it is mutually exclusive, and they are independent. If that's all true, well then, hey, all the binomial conditions apply, and NP and Q are both greater than or equal to 5, well then, hey, our sample proportion will be normally distributed, centered around the true population proportion or population probability, and we'd have a standard error of p bar of p 1 minus p all over n. right? Where again, you'll see that sometimes instead of p, you'll see that as pi. Pi 1 minus pi all over n. So same idea going on here as what happened with x bar, is we said, hey, we could always standardize if all of those assumptions are true. We could go p bar to z such that, hey, z equals p bar, I'll use pi, minus pi, all over our standard errors, pi 1 minus pi all over n. And so, hey, if we don't know what pi is, and that is we just have our point estimate, sometimes our point estimate will be pretty accurate. It'll fall most of the time pretty close to pi. But hey, we could get point estimates out here. We could get point estimates out there, right? We could get these extreme values occurring as well. So that is what we want to do. Same kind of idea. We want to say, hey, I have this point estimate. I have this value of p bar. What is my plus or minus uncertainty? Do I cover my true population proportion given this uncertainty? Such that, hey, if I did a 90% confidence interval, 9 out of 10 estimates would cover that true population proportion. 95%, great. 19 out of 20 would cover that true population proportion. 99%, 99 out of 100 would cover that true population proportion, right? So again, what I can do is I can rearrange this, I can solve, but as we go through that process, we'll notice a bit of a problem arising. And we'll go through that process there. So, okay, again, what we're going to get, we'll go through that whole rearrangement, and we'll get pi will be equal to p bar plus or minus z standard errors. And here's the problem. Pi 1 minus pi all over n. And it's like, uh-oh. We're saying, hey, our estimate of pi is dependent on pi? Uh-oh, right? We don't know what this is. That's why we're saying, what is our fuzz around that likely value? If we knew what our population parameter was, we could just say we know exactly what the fuzz is. We know exactly how wrong we are. But we don't, right? So, uh-oh, how do we correct this? Well, we don't know what pi is, but we do know what the most likely value of p bar is, right? And we say, hey, look at this distribution. We don't know what pi is, but we know that, hey, if I pull out a estimate of p bar, the most likely value for me to pull out right there is pi. So that is, well, in absence of knowing what the true population proportion is, we might as well just use our sample proportion, p bar. Okay, so in that case there, here we go. We have our estimate as to what it is. Great. From here, well, we'll have a sample proportion, sample proportion, sample proportion. We'll have our sample size that we collected in order to get that sample proportion. And then we'll have the Z value that goes along with our level of uncertainty. So again, 99, 95, 90, or some other fun one that we could come up with, and we'd work through it in that kind of way. So let's take a quick example, a quick look at this. And because, hey, at the time of going through this, it was election season. We had the provincial election. We had the US presidential election. Big thing in these elections are polling, right? Polling, 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 polling. And as they are polling, they're pulling out sample proportions. They're asking people, hey, who would you vote for? Who would you vote for? And let's say that we have candidate, we'll say we have candidate, let's use a number or a letter that we're not using a lot of. We'll say candidate M. Okay, and so we're doing our polling, and we find that, hey, we polled something like 100 people, and we find that 55% of the people that we polled support candidate M. They're saying, yeah, you know what, if I were to vote today, I would vote for candidate M. Cool. But keep in mind, this is a sample proportion. We're trying to get an estimate as to what the true population proportion is. That is how many people altogether come election day will vote for candidate M. But we don't know that, right? We can't ask everybody today. I mean, if we could, that'd be the election itself. So instead, we're just going to poll. We're just going to ask these 100 people. And from these 100 people, we're going to say, great, this is representative of the greater population. As long as we engage in correct random sampling, this will work. And we can then say, okay, 55% say that they're going to support candidate M, but what's the fuzz on that? What's my plus or minus, right? And so let's take a look at that. Let's say that we want to do this for a 99% confidence interval. That is, we want to be very confident in our results as to where these will be. So, okay, let's figure that out. What is my Z for a 99% confidence interval? Well, to do that, right, again, to find that 99%, we're going to take 99, we're going to divide it by 2. That's going to give us a probability of 0.4950. What we want to then do is we want to jump to our stats table and we want to find out, hey, what Z value is attached to that. So we jump to our stats table, we're looking for 0.4950. As we're looking for 0.4950, we get we already looked this up. We get 2.575. 2.575. So that's plus or minus 2.575. That's my Z value. To then calculate, I'm going to be going P bar plus or minus Z square root of P bar 1 minus P bar all over N. So, okay, let's work that out. P bar is 55%, 0.55. Plus or minus 2.575 times my standard errors. So my standard errors are 0.55. 1 minus 0.55, that's 0.45, all over my sample size of 100. Okay, especially for proportions here, we have a lot going on. I really recommend you calculate this in stages. The way that I typically do it is I calculate the standard error first. I do standard error times my Z value to get my fuzz, and then I work out the final. So let's do that. We have 0.55 times 0.45 divided by 100. We take the square root of all that, and that gives us 0.55 plus or minus 2.575, and then my standard errors work out to be 0.0497. We'll carry around these extra few decimal places just for this time here. Okay, working out this bit here now. Working out my fuzz, let's just make some more room to work with. We're going to have 0.55 plus or minus my fuzz, so 0.0497 times 2.575 gives me plus or minus 0.128. Yeah, we'll go like that, 0.128. So that is, if I work out, I'm saying, hey, I calculated a value of P bar of 55%. I have my fuzz, my uncertainty around that estimate, and I can now work out, okay, the true population proportion, 99 out of 100 times would fall within this range. So let's work that out. 0.55 minus 0.128 gives me on the low side 0.422. On a high side, I'm going to have 0.55 plus 0.128, and I'm going to have 0.678. And in this case here, what we really see, the big kind of takeaway in this confidence interval is, although we said, hey, look at our polling, we have 55% support for candidate M. Woo, looks like candidate M's in the lead. Great, maybe. Once we incorporate our fuzz, once we incorporate our uncertainty into this, we find that, hey, wait a minute, it might be that candidate M has as little as 42% of the popular vote. Mind you, it might be as well that candidate M has as much as 67, almost 68% of the popular vote, right? That is, yes, we have this estimate of P bar, but there's a lot of fuzz, there's a lot of uncertainty around this estimate. And this is really the part where we have to be careful. This is where when we're looking at the news, when these polls are being released to us, and the same can be said about our sample means as well, all that ever gets reported in the media is our point estimate, is this value of P bar. And they say, hey, look at that, 55% support. That is a sample statistic. Because it's a sample statistic, there is fuzz, there is uncertainty. And because of that uncertainty, you can't trust it just as it is. There is some fuzz as to what it might truly represent, as to where that true population mean might actually fall. Or sorry, in this case here, population proportion, where that true population proportion might actually fall. So where you need to be wary with that. Okay, so that's our idea with our population proportion. Our sample proportion is a point estimate, and then the confidence interval around our sample proportion being collected. What we're going to finish off with is we're going to be finishing off with, again, our confidence interval around X bar, but this time confidence interval around X bar when sigma X is unknown. That is, we don't know what the true population standard deviation is. We don't have insight into this. We're not very sure as to what is going on here. Turns out it's not the end of the world. If our population standard deviation is unknown, well, what we can do is we can estimate it. And we can estimate it using our sample standard deviation, right? But okay, here's the problem. Mu of x is unknown, and we are estimating this with x bar. So, okay, x bar is a random variable that has its own distribution around the true population mean, right? So, okay, there's some uncertainty there. And we said, hey, this was normal when sigma was null. Well, it turns out that, hey, this sample standard deviation, it is also a random variable, right? Every time we pull out a sample, we're going to get a different sample standard deviation. Each of them are an estimate of that, but each one of them has some sampling error associated with it. That is, hey, if we're estimating X bar, if we're estimating our standard deviation, we're compounding these sampling errors. We have a lot of uncertainty. With this, when sigma X is unknown, X bar is not normal. That is, X bar will no longer be normally distributed because we're just adding too much error, right? We're adding too much error. X bar, we have some sampling error. Standard deviation of X, we have some sampling error. So X bar is no longer normally distributed. Oh no, seems like we have a problem. And yeah, truthfully, we do. But what we can do is, while X bar is no longer normally distributed, X bar is now going to be T distributed. And students' T distribution, luckily, is very, very similar to the normal. The student's T distribution, let's draw it out here. The student's T distribution, so here would be T n minus 1, is bell curved, so just like our normal is, and it is centered around 0, and it has a standard deviation of 1. So seems very similar to our standard normal, right? Or Z in that case, right? Or Z was centered around 0 and had a standard deviation of 1. The difference with the T is how many standard deviations are in these tails. And that is entirely dependent on our degrees of freedom, right? N minus 1, these are our degrees of freedom. Sample size minus 1. When our sample size is really, really small, well, our T distribution has lots of area out in these tails. That is, the tails would be really thick. We would imagine, right, if we had a really, really low sample size, so let's say we had, I'll do it in yellow here, a sample size of 5, we would have a distribution that looks something more like this. Right? Lots of observations occurring in those tails. Meanwhile, as the sample size gets large, as it increases, well, as it increases, the tails begin to shrink, the tails begin to come in, and as our sample size gets larger, as our sample size approaches infinity, well, our t-distribution actually approaches our normal. So in that case there, it's not the end of the world. They're actually extremely similar. They're both asymptotic to the axes. They're both symmetric. They're both all of these other kind of characteristics. The big difference is the probability in the tails. And the t-distribution has a lot more likelihood of witnessing extreme values. That is why we have thicker tails, more probability, more values falling farther away from that mean. Okay. In this case here, we are going to have a different t-distribution for every single sample size that we have, right? Because so our normal, right, we said, hey, our normal was determined by mu and sigma. Great, cool. And we just standardized that such that z was now just going to be always a normal with 0 and 1. What we see with the t, well, we already have 0 and 1. But how much we have in our tails is determined by our degrees of freedom. And so in that case there, we're going to have a different t-distribution for every possible degree of freedom. We're going to have one t-distribution if we have 5 degrees of freedom. We're going to have a different t-distribution if we have 10 degrees of freedom. On and on and on and on. So in this sense here, our t-table looks very, very different than our standard normal table. And let's take a look at that. Let's suppose that we wanted to, let's take a look at how x becomes t distributed. So we're going to have x bar and x bar, let's take a look there. We're going to say that that is a t. You're like, but Keith, it looks like a normal. Yeah, it does, right? That's the big thing with the t, is they do look exactly like a normal. We're going to be centered around our mu. Let's say this is 500. And we're going to have our standard deviation of x bar. In this case here, that's more of our standard or sample standard deviation of x bar. And that's going to be equal to our sample standard deviation of x all over root n. So you're like, wow, that's very similar. The only difference is we're using s instead of sigma. Exactly, right? Exactly. It's very, very similar. We just have this sample standard deviation of x instead of sigma x. So let's say in this case here that I have an estimated sample standard deviation of, let's say 50, and I pull out a sample size of 25. Okay, sample size of 25, I need to have an assumption here, right? I have to assume that x is symmetric, right? That is, symmetric distribution of x allows me to get away with an n of greater than 10. I would need an n greater than 30 without an assumption, right? My central limit theorem still has to apply here, that whole n greater than 3, 10, or 30. So this assumption needs to be made. Okay, so if that's the case, what do I have? I'm going to have 50 all over root 25. 50 over 5, well, give me a standard error of 10. Okay, say I wanted to know, okay, what value of x bar such that I would be in the top decile, right? Such that, hey, 10% of values are bigger than that value of x bar. Well, okay, the way that we would typically do that is we would standardize, and typically we would go and we'd standardize to a z. But no, we can't do that this time. And the reason we can't do that this time is because the standard deviation of x is unknown. We've had to estimate it with our sample standard deviation. So that is what we need to do, is we need to still standardize, but we're going to standardize instead this time with a t n minus 1. So okay, a t n minus 1, we have an n of 25, so we're going to be standardizing to a t24. Okay, just keep that in mind right now, t24, and we would have to go and find our value of t. Instead of a value of z, we're looking for a value of t, right? Okay, what about our standardization? How would we do that? Okay, again, don't fret. It's not going to be a new formula. All we can say is, in this case here, our standardization, t is going to be our random variable of interest, so x bar minus our mean all over my standard errors. So in this case here, sample standard deviation all over root. Right, in this case here, you say, wow, that's very similar, because yes, it is. If we compare it, our z was x bar minus mu all over the population standard deviation all over root n. Right, the only distinction between these two standardizations are the standardization statistic, t versus z, based off of, do we have a sample or do we have a population standard deviation? That is the deciding factor. What do we know about the standard deviation? Do we know the population or do we have to estimate it? So great. That's that one there. How do we find this value of t though, right? How do we find this t24? Well, let's jump over to our t-table and let's go take a look. So our t-table, again, that's going to be in the back of our textbook. We had our normal table, and if you just keep scrolling a bit farther down, you get the student's t distribution. And again, it's important to look at the picture here as to what exactly is happening. And in this case here, we witness that, hey, it's saying there's 0, there's some t distribution with v degrees of freedom. So they use v to denote our degrees of freedom. And a, this little alpha, rather, is the probability that you're looking up. So that is, with our normal, we were finding the probability between t and 0. With our t distribution, we're finding the area of the probability between the t and positive infinity, the right-hand tail. Now again, it's a symmetric distribution. So if we had a negative value, well, it would be correspondingly negative. A little bit different as well, right? In this case here, we have across the top here, these are our values of alpha. So this is saying, hey, alpha of 10%, alpha of 5%, 2.5, 1, 0.5, 0.1%, right? So values of alpha being relatively small as we go through this. Going through it then from here, what would we want to do? Well, our question, what we were looking for is we were saying, hey, what would be the value of x bar to be in the top decile? That is, if we jump back to take a look at that, we said, hey, we wanted x bar or greater to be 10%. That's our alpha, right? That's our alpha. We wanted this guy here to be 10%. So, boom, there we go. Now that we have the probability, right? In this case here, we only have, what, 6 possible probabilities to look up. As we go down, we get our t values, right? So let's compare and contrast that for a second. Up here, we had our probabilities in the middle, our z-score, our z-statistics along the outside. For the t, we have our t values in the middle, we have the probability in the tail along the top, leaving us this guy here. This left-hand column, this is our degrees of freedom. This is our degrees of freedom. So in our case, we're looking for an area of 10% with 24 degrees of freedom. That gives me a t statistic of 1.318. So we could record that, 1.318. 1.318. And from there, okay, we would know, there's my t value, 1.318 equals x bar minus my mu of 500 all over my standard errors. What did I say my standard errors were? 50 over root 25, 10. And from here, I can work through to find that out. So 1.318 times 10 plus 500 gives me 513.18 equals my value of x bar. So we can calculate in very similar ways, right? We're a little bit more constrained using tables for our t statistic, for our t distribution, but we can calculate things in much the same way if we had our sample standard deviation rather than our population standard deviation. Okay, so that was our point estimate, right? Keep in mind, just one value of x bar is the point estimate. What if we wanted to know what our fuzz was around this estimate? Say, okay, hey, cool, we just calculated 513.16. What is the 95% confidence interval around that guy? Right, so okay, we had x bar of 513. Let's just say 513. I don't want to be writing decimals. So x bar of 513. We had a sample size of 25, and we had a sample standard deviation of 50. And I want to calculate this 95% confidence interval. Well, same ideas we've done for x bar before, same ideas we did for p bar. The way that that's going to work out is our confidence interval, and this time here it's going to be a t, is going to be, right, and this is the confidence interval around mu. This will be x bar plus or minus our t n minus 1, so this is going to be a t 24, and I'll go for a 95%, all over sample standard deviation root n. So, hey, exactly the same as we had it before. Difference is this used to be a z because that used to be sigma. So only difference there. So starting to update our numbers. What do we have? We have x bar of 513. Again, I'm just using 513 because I'm being lazy. I don't want to write decimals. So just changing it a bit there. Plus or minus some t. I'm just going to leave that blank for now. We'll come back and fill that in. All over my standard errors. So that's going to be 50 all over root 25. What's this t? Well, okay. Let's keep in mind how we did it before. We said, okay, hey, 95% confidence interval. Let's just draw that here. We said, okay, 95% confidence interval. There was my mean. I did something like this and like that, such that all of that was 0.95. If all of that was 0.95, I said, hey, this was 0.025. This was 0.025. Well, okay, keep in mind that that was my alpha from that t-table, right? That was that tail that was left over. So in this case here, what I want is, I have an alpha in this case, 95% confidence interval. I have an alpha of 2.5%. So let's jump over to our t-table and look up the corresponding t24. So T24 for 2.5%. So up to the top, 2.5% is my third column. Going down, T24 would be 2.064. So taking a look at that, let's jump back. 2.064 would be that corresponding T statistic. So working this out then, we have 50 over root 25. Well, we've already worked that out. That guy works out to be 10. So 10, we have 2.064, and then 513 plus or minus. So that gives me 513 plus or minus my uncertainty plus my fuzz. So 10 times my t statistic of 2.064. That's 20.64. So okay, we're saying, hey, we've obtained a sample mean of 513. We think, hey, this is a good estimate of our true population mean mu, but we have this fuzz, this uncertainty as to what the true population mean might be, right? 95% of the time this would cover it, and we can work out what that band is. Lower limit, upper limit. So 513 minus 2064 gives me on the lower side 492 536. And on the upper side, 533, 64. So there's my 95% confidence interval. Saying, okay, yep, I got a value of my true population mean of 513. I'm saying, okay, given my fuzz, given my uncertainty, 95% of the time I would be pulling out a sample such that the true population mean would be somewhere in there. In this case, what did we say our true population mean was, right? We actually played around with that. We made up a value for it. We said our true population mean was 500. That is this value of x bar. If we wanted to visualize it, we're saying, hey, we calculated x bar to be 513 and saying, okay, this represents a true population mean from about there to about there, right? Such that, what were those values? We had 533 on the high side and what, something like 492 on the low side. And sure enough, our true population mean does fall within that confidence interval, which, yay, sure enough, this sample that we pulled out is one of those 19 out of the 20 that covers the true population mean. Okay, so those are our confidence intervals. This is the introduction to them. We've seen each of them. Let's kind of take a look at each one just on its own. So we have x bar when sigma is known. I can't write. When sigma is known. Okay, so confidence interval x bar when sigma is known, we would have x bar plus or minus z, standard deviation of x all over root n. Compare that to x bar for when sigma is unknown, and we would have x bar plus or minus our t n minus 1 s of x root n, right? So the big difference, if our sample standard deviation, our t statistic. Finally, we had p bar, right? Our confidence interval for p bar. This was not dependent on whether or not something was known. P bar was always normally distributed if our conditions were met. And so in that case there, we had p bar plus or minus z root, and we'll use p in this case, p 1 minus p all over n. And okay, I said in there, hey, p bar is always normally distributed if the conditions are met. Let's write down our conditions for each case here. So for p bar, we need np, nq to be greater than or equal to 5, as well as our binomial conditions. Okay. For these guys, again, for x bar to be normally distributed, or t distributed even, we need the central limit theorem kind of situations to hold. N greater than 3, n greater than or equal to 10, n greater than or equal to 30. That is when x is normal, we can just get away with a sample size of 3. We need greater than or equal to 10 when x is symmetric. And then finally, greater than or equal to 30 if x is anything, right? If x is unknown. If we have a sample size greater than 30, it doesn't really matter what we assume or what we know about x. We're good to go. So these are the conditions that need to be met in order to go through with them. Okay, next video, what we're going to be taking a look at is how we determine appropriate sample size, right? Should I get a sample size of 30? Should I get a sample size of 100? Should I get a sample size of 10? What's my required, what sample size should I aim for? What we're also going to be taking a look at is what happens if we pull out too large of samples. And that there's going to be taking a look at what we have as our finite population correction factor. Not to be confused with our continuity correction factor, right? So two different things there. So we'll be taking a look at those two in the next video. As well, what we'll do to wrap up this week worth of videos, we'll take a look at a whole bunch of examples of calculating confidence intervals. And mechanically, confidence intervals are pretty easy to work through, right? It's just working through this. In practice, they can be difficult, and they can be difficult because you need to determine which out of these three you're utilizing in the question, right? Very rarely will it just say, hey, calculate the confidence interval around X bar when sigma is unknown. You have to read the question. You have to determine, hey, I'm dealing with X bar, a sample mean, and then you need to infer, is sigma known or unknown? That is, do I know the population standard deviation or not? So that inference needs to come from that question, a bit of critical thinking, and you need to figure, okay, what tool do I pull from the toolbox? Again, as I've said a few times, that is the most difficult part of this course. So 2 videos this week, or 2 more videos beyond this one this week. One taking a look at a few more concepts, another one just taking a look at a bunch of examples. If you have any questions on calculating confidence intervals, though, feel free to reach out to me, D2L frequently asked questions, or send me an email. Thanks.